Welcome to 16th lecture. In this lecture we will study or we will compare the two formulas that we can use to compute sample variance. In last lecture we studied that the correct formula to compute sample variance is this, in which we have n minus 1 in the denominator. This is the correct formula, but someone can argue that why n minus 1, why not n? So in this lecture we'll answer why this should be n minus 1, why not n, right? There are other theoretical reasons for this that we will study in future lectures, but in this lecture we will go through a Python simulation, a programming simulation, in which we will generate some data and then we'll draw random samples out of it, and we'll demonstrate that using n minus 1 in the denominator, using this correct formula, produces values that are closer to sigma squared. What is sigma squared? Sigma squared is variance of population, and we have already studied that variance of sample is used to estimate the variance of population. So using a computer simulation, we will show that using n minus 1 in the denominator, using the correct formula, we will get results that are very close to the variance of population compared to the incorrect formula in which we have n in the denominator. So we'll compare the two formulas. Which two formulas? These two formulas, the correct formula versus the wrong formula, and we'll see that using the correct formula we will get good results, results that are closer to sigma squared for samples of small sizes. So this is actually we will do in this lecture, or what we are going to do is we are going to run a Python simulation in which we will first generate a population of some thousands of numbers, and then we'll draw small samples out of it, samples of user's choice. How many samples? User will decide the samples, the number of samples to be collected, and the size of each sample. This will also be selected. That will also be selected by the user. So user will select two things: number of samples and the size of each sample out of the population. But first user will select the size of the population. Of course that should be large. And we'll see that using this formula, the formula that for which we have n minus 1 in the denominator, produces results as squared that are closer to the variance of the population. So let's move on to the simulation. This is a simulation I wrote for you. These are some imports, and first we will ask our user to enter the total number of measurements he or she wants in the population. That may be 1,000, 2,000, 5,000, or 10,000, but that should be large. And then we will use the random function in taken from the random class, and we will generate integers that have values between 0 and 99. So suppose the user says that I want to generate 1,000 samples, so the value of each sample would be 1,000 numbers or 1,000 measurements. So the value of each measurement will be between 0 and 99, and then we'll draw a dot plot for that population to show that what is the distribution of the population that the user has generated. And then we will draw some samples. So first we'll ask user to input number of samples to be collected, this one, number of samples 1, 2, 3, and then we will ask our user to enter number of measurements in a sample, the size of each sample. What should be the size of each sample? This one. What should be the size of each sample? So first we will ask user to enter the number of measurements he or she wants in the population, and then the size of the sample, the number of samples to be collected, and the size of each sample. And then what next the program will do is that it will create variance, it will generate variance on each sample, variance of each sample using two formulas. The dot variance formula produces variance using n-1 in denominator, and the dot p variance formula, the dot p variance function, it produces variance with n in denominator. So variable names are self-explanatory, right? And then we will compute the variance of population using this p variance function, and then we'll compute mean of the samples of all these samples. Which samples? These samples. So the variance computed on this sample, all these samples, and we'll compute the mean of that variance, so that we come up with one value of variance of all samples, one variance of all samples. And that variance, we will compare that with the variance of the population to see that out of these two formulas, this one with n-1 in denominator and this with n in denominator, which of the two is closer to the population variance, the variance of the population. So let's move ahead and run this simulation. Right, so let's run it. So it is prompting us to enter total number of measurements in the population. Let's say, set it 1000. So we want 1000 measurements in the population, and this is the dot plot our program has generated for. So the values are from 0 to 99. So this is the dot plot giving us an idea about the distribution of numbers we have generated. And then it is asking for the number of samples to be collected, this one, number of samples. So let's say we want 10 samples. So now this program is asking about the number of measurements in each sample. I mean, the size of each sample. How large do you want each sample to be? Since we are working with small samples, let's say 4 is the size of each sample. So what it's going to do is, it says that the variance of the population computed on 1000 numbers is 823, and the variance of 10 samples using n-1 in denominator, the correct formula is 667. The percentage error using this formula is 17.72, whereas using the second formula, the incorrect formula using n in denominator, the variance is 508.29, producing a percentage error, a larger percentage error, 38.29. So this means this formula with n-1, it produces a value of variance that is closer to the variance of the population with 17% error. Let's run it once again. Let's run this program once again, and this time let's produce 2000 samples, and this is the dot plot of 2000 samples we have generated. And then number of samples to be collected, let's say we want to collect 8 samples, and the size of each sample, maybe we want small samples, 3. So the percentage error is quite larger for n-1. Okay. All right, let's run it once again. Let's run it once again for 2000 samples. Right, 2000 samples. This is the dot plot, and maybe we collect 10 samples. Size of each sample is now 4. So now we have this n-1 denominator. It produces 5.5 percentage error, 5.55%, and for n, this is, if you use n in denominator, the incorrect formula, it produces a larger percentage error. Okay, let's run it once again, and once again for how many points? Maybe for 3000 points, for 3000 measurements in the population. Oh, this is the dot plot, quite rich, quite busy dot plot. And number of samples to be collected, maybe this time you want to collect 12 samples, and the size of each sample is small, 4. So it produces, using n-1 in denominator, it produces an error 4.45, and using the incorrect formula it produces a larger error, 28.3. Right, let's run it once again for how many samples, let's run it for 5,000 samples, 5,000 measurements. 5,000 measurements. This is our 5,000 measurements. So this is the dot plot. And then how many samples do you want to collect? Maybe I want to collect 11 samples, and size of each sample should be small, 5. So the correct formula, using n-1 in the denominator, it produces a smaller error, 7.99, and this produces a larger error, 26.6. So it's a fun. You can make use of this code to draw, to select population size first, and then the number of samples and the number of measurements in each sample, and you can experiment it with different settings by setting these 3 numbers, this one, and this one. So you can try different values of these 3 numbers and you will get some interesting results. I'll share this on our WhatsApp group. I'll share this code on our WhatsApp group, so you can try, and you can play with this, and you can try different settings, and you'll see that out of a larger population, if we collect a reasonable amount of samples and the sample size is small, the percentage error produced by this formula using n-1 denominator is smaller compared to the formula that has n in the denominator, giving us a good reason to use n-1 in the denominator to compute sample variance. Right, that's all for this lecture. Thank you.